A wildfire in Utah did something on August 2026 that ordinary fires cannot do. It built its own thunderstorm. Smoke and superheated air surged upward. Clouds rapidly expanded above the flames. Lightning flashed inside them, and two towering bursts climbed toward the top of the atmosphere. Hours later, another unusual burst appeared before sunrise. The next day, scientists sent an aircraft after the smoke and intercepted it roughly 12 kilometers above Earth. What they were chasing was a pyrocumulonimbus cloud, one of the most extreme connections between wildfire and weather on the planet. These clouds, usually shortened to pyrocumulonimbus, can form when a fire releases heat so rapidly that the atmosphere above it becomes violently unstable. Instead of smoke simply spreading sideways, hot air accelerates upward like a giant chimney. As it rises, it cools, water vapor condenses, and a towering cloud begins to form. If the updraft becomes powerful enough, the cloud can develop into a full cumulonimbus thunderstorm. The fire has effectively built its own weather system, complete with strong winds, heavy precipitation, hail, and lightning capable of igniting new fires beyond the original burn area. NASA calls pyrocumulonimbus some of the least understood forms of severe weather, which is why aircraft are now deliberately chasing them across western North America. The 2026 campaign is called INSPYRE, the Injected Smoke and Pyrocumulonimbus Experiment. NASA, the U.S. Naval Research Laboratory, NOOO researchers, the National Science Foundation, universities, and other partners are combining aircraft, satellites, ground instruments, and computer models to answer a deceptively difficult question: why do only a small fraction of wildfires suddenly become powerful enough to generate these enormous storms? The mission is also investigating what happens after pyrocumulonimbus smoke escapes the lower atmosphere, because the largest events can inject particles into the stratosphere, where ordinary wildfire smoke rarely reaches. The Widemouth 2 fire in Utah provided one of the campaign's first opportunities. Lightning ignited the fire on July 27. It remained relatively limited for several days, but on August 2, hot, dry conditions and intense winds caused it to more than double in size. NASA's Aqua satellite passed overhead after the fire had generated two pyrocumulonimbus bursts. Invisible imagery, a towering column of smoke and cloud, cast a dark shadow over the lower smoke plume. Infrared observations measured cloud top brightness temperatures below -40 degrees Celsius, a commonly used indication that the cloud had climbed into the extremely cold upper troposphere and, in some cases, may have penetrated into the stratosphere. Then something even stranger happened. Before dawn, the fire produced another pyrocumulonimbus. These early morning events are unusual because pyrocumulonimbus often benefit from daytime solar heating, which helps make the atmosphere more unstable. In this case, scientists believe the atmosphere already contained enough moisture and instability for deep convection to develop without the usual afternoon heating. Multiple pyrocumulonimbus from the same fire in a single day also demonstrate why they are difficult for firefighters and weather forecasters. The fire is no longer responding only to the surrounding weather, it begins altering that weather itself. On August 3, researchers reacted quickly. An NSF and INSPYRE Gulfstream V aircraft left Colorado and flew toward a plume from Widemouth 2 that had drifted over New Mexico. The aircraft intercepted the smoke at about 12 kilometers, or roughly 8 miles above the surface. That altitude is near the upper reaches of the troposphere, much higher than the levels typically sampled during ordinary wildfire research, and high enough that the smoke may behave very differently from pollution near the ground. Measurements from these flights are especially valuable because satellites can show researchers where a plume is and how cold its cloud tops are. But an aircraft can physically enter the air mass and measure the particles and gases inside it. The mission uses multiple aircraft for different purposes. NASA's ER-2 is a high-altitude research plane capable of flying above many storms and carrying instruments that observe fires from a perspective similar to a satellite. The NSF/NKR Gulfstream V can sample the atmosphere directly, Ground-based instruments and satellites then provide the larger picture. NOAA's involvement includes measurements of soot and other particles aboard the Gulfstream Vive, while NASA's FireSense program is flying advanced infrared instruments capable of observing active fires. Together, these platforms allow researchers to watch the same event from the flames near the surface all the way into the upper atmosphere. The reason scientists care about the highest smoke is that the stratosphere is very different from the lower atmosphere. Most weather occurs in the troposphere, where clouds, rainfall, and turbulent mixing can remove smoke relatively quickly. The stratosphere above is much drier and more stable. If a pyrocumulonimbus pushes particles across that boundary, there may be little rain available to wash them out. Smoke can spread across continents, circle the planet, and persist for months or even longer. Once there, the smoke does more than reduce visibility. Dark particles absorb sunlight, while other aerosol particles scatter it. Both processes affect how energy moves through the atmosphere. Smoke can warm particular atmospheric layers while reducing the amount of solar radiation reaching lower levels. Researchers are also investigating interactions between wildfire aerosols and stratospheric ozone chemistry. NASA's Atmospheric Research Program states that increasing wildfire size and intensity could amplify pyrocumulonimbus-driven smoke injection into the stratosphere enough to produce measurable changes in Earth's radiative balance. The scale is larger than the rarity of these storms might suggest. Satellite researchers estimate that wildfires generate about 70 pyrocumulonimbus worldwide each year. Since scientists began systematically identifying them, more than 700 events have been cataloged. By mid-2026, at least 13 had already been identified in the continental United States. Researchers also estimate that wildfire-driven pyrocumulonimbus may contribute as much as a quarter of the black carbon and organic aerosol found in the lower stratosphere. Across an entire wildfire season, the total amount of particles delivered upward by repeated pyrocumulonimbus may rival the injection from major volcanic eruptions. That comparison is surprising because volcanoes have long been recognized as one of the few natural processes capable of forcing huge quantities of particles directly into the stratosphere. Large eruptions can temporarily change global temperature by producing sulfur-rich aerosols that reflect sunlight. Pyrocumulonimbus work through a different mechanism and carry different material, but they demonstrate that intense wildfires can connect Earth's surface with atmospheric layers normally isolated from ordinary smoke. A forest fire that begins between trees can ultimately change atmospheric chemistry more than 10 kilometers above the ground. The clouds are dangerous long before the smoke reaches those heights. A pyrosp contains intense vertical winds. Its lightning can ignite spot fires kilometers away. Rapid shifts in wind around the storm can change the direction of flames at the surface. Pilots may face smoke, turbulence, cloud, and unpredictable convection simultaneously. For firefighters, this creates a feedback that is difficult to manage. The hotter the fire becomes, the stronger the convection can grow, and the resulting weather may then make the fire even harder to control. NASA specifically describes improved real-time measurement and forecasting of these events as a major goal of INSPYRE. Yet researchers still cannot reliably explain why one extreme wildfire generates a pyrocumulonimbus while another apparently similar fire does not. Temperature differences between the surface and upper atmosphere influence instability. Wind structure can either organize or destroy a rising plume. Fire size and heat release matter, but even those factors are not enough on their own. Scientists also do not fully understand why some pyrocumulonimbus produce much more lightning than others, or what determines exactly how much smoke reaches the stratosphere. That uncertainty is precisely why the 2026 flights are unusual. Satellites have observed these storms for years, but direct sampling soon after formation is far less common. INSPYRE can compare the physical fire below, the structure of the cloud, the chemistry of fresh smoke, the particles reaching high altitude, and the plume after winds carry it far from the original fire. Researchers can then test whether forecast models correctly reproduce what actually happened. NOAA describes the experiment as an effort to establish the physical links between pyro-CB initiation, smoke injection into the upper troposphere and lower stratosphere, and the consequences farther downstream. The campaign comes as wildfire behavior is becoming increasingly important to atmospheric science. NASA states that increasing wildfire size and intensity could increase pyro-CB smoke injection. That does not mean every future fire will produce one, and scientists are still working to determine how climate, vegetation, and weather combine to change their frequency. But if major pyro-CBs become more common, understanding them becomes necessary not only for firefighters and local forecasts, but also for models of atmospheric chemistry and Earth's energy balance. The Widemouth 2 event therefore represents more than one wildfire in Utah. It gave scientists a chance to follow a chain of events that is usually difficult to observe from beginning to end. Lightning ignited vegetation. The fire intensified. Extreme heat drove air upward. Water vapor condensed. A thunderstorm grew from the smoke. Lightning formed inside a cloud created by the fire itself. That cloud carried particles toward the top of the troposphere, and the following day an aircraft intercepted the plume 8 miles above Earth. At first glance, wildfire smoke seems like something that should remain close to the ground and drift away with the wind. Pyrocumulonimbus clouds reveal a much stranger system. Under the right conditions, a fire can become powerful enough to alter the atmosphere above it, create a storm, and build a vertical transport system connecting burning vegetation directly to the stratosphere. NASA's aircraft are chasing those storms in 2026 because the crucial questions are no longer whether fires can do this. We know they can. The mystery is exactly how they cross that threshold, what they carry upward, and how long the consequences remain in the atmosphere after the flames below have disappeared.